The James Webb Space Telescope, JWST, is not only larger than its predecessor, the Hubble Space Telescope, but it is also equipped with advanced instruments designed to study the universe in unprecedented detail. One of its key capabilities is its ability to observe in the infrared spectrum, which allows it to peer through cosmic dust clouds and observe objects hidden from traditional optical telescopes. This capability is crucial for studying the formation of stars and galaxies, as well as for detecting and characterizing exoplanets. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb's suite of instruments includes the Near-Infrared Camera, NIRCam, the Near-Infrared Spectrograph, NIRSpec, and the Mid-Infrared Instrument, MIRI. These instruments cover a broad range of infrared wavelengths, enabling scientists to study a wide variety of astronomical phenomena, from the earliest galaxies in the universe to the atmospheres of exoplanets. One of the most exciting prospects for Webb is its potential to study exoplanets, planets orbiting stars outside our solar system. By observing these distant worlds in infrared light, Webb can analyze their atmospheres for signs of life or habitability. This includes detecting molecules such as water vapor, carbon dioxide, and methane, which are essential for supporting life as we know it. Webb's ability to study exoplanets extends beyond mere detection. Its high sensitivity and resolution allow scientists to analyze the chemical composition of exoplanet atmospheres in great detail, providing insights into their formation and evolution. This information is crucial for understanding the diversity of planetary systems in our galaxy and beyond. Another key objective of the James Webb Space Telescope is to unravel the mysteries of cosmic origins by studying the earliest galaxies that formed in the universe. Webb aims to shed light on how galaxies evolved from their initial formation to the present day. Its infrared capabilities are particularly suited for observing these distant galaxies, whose light has been stretched to longer wavelengths due to the expansion of the universe. Webb's deep field observations, similar to Hubble's famous ultra-deep field, will capture images of some of the faintest and most distant galaxies ever observed. These observations will provide astronomers with valuable data on the formation of galaxies and the processes that drove their evolution over billions of years. In addition to studying galaxies, Webb is also poised to revolutionize our understanding of star formation and the formation of planetary systems. Dense regions of gas and dust, known as molecular clouds, are the birthplaces of stars and planets. Webb's infrared vision allows it to peer through these dusty veils and observe the processes that give rise to new stars and planetary systems. The telescope's ability to resolve fine details in these star-forming regions will enable astronomers to study the dynamics of gas and dust as they collapse to form stars. Webb will also investigate protoplanetary disks, the swirling clouds of gas and dust around young stars where planets are born. By studying these disks in infrared light, Webb can detect the signatures of planet formation and provide insights into how planetary systems, like our own solar system, came to be. Beyond its primary science objectives, Webb will contribute to our understanding of two of the most enigmatic components of the universe: dark matter and dark energy. Dark matter is believed to make up the majority of the mass in the universe, yet it emits no light and interacts weakly with ordinary matter and radiation. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. While Webb is not specifically designed to directly detect dark matter or dark energy, its observations of distant galaxies and their distribution throughout the cosmos will provide valuable clues about these elusive phenomena. By mapping the distribution of galaxies and studying their motions over cosmic time, astronomers can infer the presence of dark matter and its gravitational effects on the large-scale structure of the universe. Similarly, Webb's observation of distant supernovae and other cosmic phenomena can help constrain models of dark energy and its influence on the expansion of the universe. The development and construction of the James Webb Space Telescope have been a collaborative effort involving NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA). ESA provided the Ariane 5 rocket for the launch, as well as key scientific instruments and expertise. The CSA contributed the Fine Guidance Sensor, FGS, which plays a critical role in pointing and stabilizing the telescope during observations. International partnerships are essential for large-scale space missions like Webb, as they enable the pooling of resources, expertise, and scientific goals. The scientific community worldwide has eagerly anticipated Webb's launch and is poised to leverage its unique capabilities for groundbreaking discoveries in astronomy and astrophysics. In addition to its scientific objectives, the James Webb Space Telescope is expected to inspire future generations of scientists, engineers, and astronomers. Its ambitious mission and cutting-edge technology capture the imagination of people around the world, showcasing the possibilities of space exploration and discovery. Webb's educational outreach programs, developed in collaboration with educational institutions and science centers, aim to engage students and the public in the excitement of space exploration. These programs include curriculum materials, educational resources, and interactive activities that highlight Webb's scientific goals and achievements. By fostering interest in STEM, science, technology, engineering, and mathematics fields, Webb's outreach efforts contribute to building a scientifically literate society prepared to tackle the challenges of the future. The concept of the James Webb Space Telescope began after it was first recommended in 1996. 3 gatherings of scientists and specialists from public and private sectors assessed whether NASA could construct the telescope, and all 3 groups reached the same conclusion: the telescope could be built. In 1997, NASA agreed to fund additional examinations to refine the technical and financial requirements. By 2002, the organization had selected teams to fabricate the telescope's most significant hardware and formed an advisory group of scientists to assist with the design process. The telescope was officially named the James Webb Space Telescope that year, in honor of the former head of NASA who made significant contributions to the Apollo program. When engineers and scientists began building the Webb telescope in 2004, they needed to develop new technologies and techniques to meet the mission's stringent science needs. Unlike Hubble, which could be serviced and repaired from Earth, Webb would need to operate autonomously from a distance too great for Earth-based assistance. Despite these challenges, the team completed all 18 mirror segments and subjected them to rigorous testing to ensure they met the required standards. The James Webb Space Telescope was constructed and worked on from 2012 to 2013, with different pieces being built in various locations around the world. Building began on Webb's sunshield layers in 2013. These layers protect the telescope from excessive heat and allow it to function well in space. Over the next few years, Webb's various scientific instruments underwent extreme tests, including exposure to high temperatures and shaking. Simultaneously, the telescope's 18 separate mirrors were carefully placed on its backplane. These parts were assembled and tested at NASA's Johnson Space Center in Houston, Texas. In 2017, the telescope and its equipment underwent a final round of environmental tests in a giant thermal vacuum chamber to ensure they would work properly in space. Webb was finally launched into space on December 25, 2021, at 7:20 a.m. Eastern Standard Time. So, how does the telescope truly work? People often simplify space travel, but the James Webb Telescope is far from just another camera. It is designed to see things in space that are too cold or faint for traditional telescopes to detect, such as stars, galaxies, and planets in their early stages of formation. The telescope is designed to capture infrared light, which these distant celestial bodies emit most of their heat in. This allows us to study these objects in more detail. Infrared light cannot get through gas and dust, which makes it look obscure to our eyes, but Webb can see ultraviolet radiation as well as visible and infrared light. This allows it to capture images of objects hidden by dust and gas, giving us a better view of events happening far away in the universe. Its journey to space. Let's look at the steps this pivotal telescope took to get into space. The launch was the first critical step. After launch, the solar array was deployed, and 2 major deployments occurred on the 3rd day of the journey while the telescope was still in space. The major sun shields for Webb were deployed on these deployments to keep the telescope cool and operational. The positioning of these shields was crucial for the telescope's performance during its journey. On the 4th day, the payload and instrument package were moved to their final position and assembled. The sunshield was then deployed, followed by the deployment of the sunshield film cover, which revealed the tennis court-sized sunshields. The 5 pieces of the sunshield were then pulled apart, and the secondary mirror and bracket were installed. On day 10, the primary mirror wings were unfolded on day 13, giving the telescope its final shape. Once these steps were completed, the telescope was ready to begin its mission of observing distant stars and planets. The real point. What is interesting about the James Webb Telescope is that it wasn't designed to do just one thing. It was meant to tackle many tasks. Researchers like Daniel Eisenstein, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, can use telescopes like Webb to look back into the past and see galaxies when they were just beginning to form. Light travels slowly, so a planet that is far away looks older than it actually is. The telescope can examine the early history of galaxies to understand how they formed and evolved over time. Webb is excellent for studying distant galaxies because it can detect infrared light, which is stretched to longer wavelengths due to the universe's expansion. Webb's ability to capture infrared signals enables us to observe galaxies as they form and evolve, providing insights into the universe's development. Studying stars and black holes. Scientists study stars from the specific places where they are born. Stars form from dense clouds of gas and dust called nebulae. Since these clouds are so dense, visible light cannot pass through them, making it challenging to observe these regions with optical telescopes. However, infrared light can penetrate these dusty clouds more easily, allowing scientists to see into the core of star-forming regions in ways that other telescopes cannot. The Webb telescope's ability to detect infrared light will enable researchers to study these areas in much greater detail than before. Additionally, while black holes are difficult to see because they trap light, scientists study their effects on surrounding stars and galaxies. Webb's infrared instruments will allow scientists to study black holes in more detail by observing the cooler gases and stars orbiting them. Conclusion. The James Webb Space Telescope represents a significant leap forward in our ability to observe and understand the universe. With its advanced infrared capabilities, Webb promises to revolutionize our understanding of cosmic origins, exoplanetary systems, star formation, and the fundamental nature of dark matter and dark energy. As the successor to Hubble, Webb builds upon decades of scientific advancements and technological innovation, opening new frontiers in astronomy and paving the way for future discoveries. By peering deeper into space and observing in wavelengths beyond the reach of previous telescopes, Webb will unveil new insights into the mysteries of the cosmos, inspiring awe and wonder in people of all ages. As Webb embarks on its mission to explore the universe, scientists and enthusiasts alike eagerly await the discoveries that lie beyond the stars. The future of space observation. As the James Webb Space Telescope (JWST) continues its mission, it is expected to provide a transformative impact on our understanding of the cosmos. This telescope not only surpasses its predecessors in terms of technological advancements but also opens new avenues for space exploration and research. One of the major anticipated contributions of JWST is its ability to observe the universe in unprecedented detail, allowing scientists to make groundbreaking discoveries that were previously out of reach. Advancements in instrumentation. JWST's instrumentation represents the forefront of astronomical technology. Its instruments are designed with exceptional precision to capture the faintest signals from the farthest reaches of the universe. The telescope's detectors are highly sensitive, capable of picking up minute variations in infrared light that can reveal a wealth of information about distant cosmic objects. This sensitivity is crucial for studying phenomena that emit very little light or are obscured by intervening material. Moreover, the telescope's large primary mirror, measuring 6.5 meters in diameter, is composed of 18 hexagonal segments that work together to collect and focus light with remarkable clarity. This design not only increases the telescope's light-gathering power but also enhances its resolution, enabling it to observe fine details in the most distant and faint astronomical objects. Exploring exoplanetary atmospheres. One of the key areas where JWST is expected to make significant contributions is in the study of exoplanetary atmospheres. The telescope's advanced instruments will enable scientists to analyze the atmospheric composition of exoplanets with greater accuracy. This includes studying the presence of chemical signatures that may indicate the potential for life. By observing the light that passes through or is reflected off an exoplanet's atmosphere, JWST can detect and analyze various molecules, such as oxygen and ozone, which are important for understanding planetary habitability. This capability will help identify potentially habitable exoplanets and further our search for life beyond our solar system. Investigating cosmic phenomena. JWST's observations will extend to a range of cosmic phenomena, including supernovae, black holes, and galactic mergers. By examining the light from these events, scientists can gain insights into the life cycle of stars, the formation of black holes, and the dynamics of galactic collisions. For instance, observing supernovae in different stages of their evolution will provide valuable data on the processes that drive these powerful explosions and their role in enriching the interstellar medium with heavy elements. Similarly, studying the interaction between black holes and their surroundings will enhance our understanding of these enigmatic objects and their influence on galactic evolution. Educational impact and public engagement. In addition to its scientific impact, JWST is also poised to have a significant educational and public outreach role. The telescope's mission and findings will be shared through various media, including educational programs, public lectures, and interactive exhibits. These efforts will aim to inspire the next generation of scientists and engineers by showcasing the marvels of space exploration. The telescope's data will be made accessible to educators and students, providing opportunities for hands-on learning and engagement with cutting-edge science. By fostering a greater appreciation for space and science, JWST will contribute to a more informed and scientifically literate society. Collaboration and future prospects. The collaborative nature of the JWST project demonstrates the importance of international partnerships in advancing space science. Future missions and projects will likely build upon the successes of JWST, leveraging the knowledge and experience gained to tackle new scientific questions. As we continue to explore the universe, the insights provided by JWST will serve as a foundation for future discoveries, pushing the boundaries of what we know and how we perceive our place in the cosmos. The continued advancement of technology and collaborative efforts will ensure that space exploration remains at the cutting edge of scientific research, offering new perspectives on the fundamental questions of our universe.